Hello and welcome to Bay College's Intermediate Algebra online lectures. Today we're going to be looking at section 9.1, which deals with translations, which are also known as transformations of functions. When it comes to functions, we need to know our library of functions. They're also called our parent functions. The first one we're going to look at is essentially a parabola, which is an x squared term. Y equals f of x in function notation equals x squared. This is our parent function. And we should have a general concept of the shape of these functions. A parabola starts at the origin and goes this way and this way. It has symmetry with the y-axis. This is the graph of our parent function of a parabola, f of x equals x squared. And what we're going to look at is how we can transform these. The first thing we're going to look at is a horizontal shift. So if we go over here, we'll see y equals f of x plus 2. What happens to this graph if we add 2 to some x value? So instead of having x squared within these parentheses, I have x plus 2 quantity squared. This is called a horizontal shift. And if we recall from section 7.5, this is our h value. So this is our horizontal shift, an h value. Now, if I want to do this, I really only have to graph one point, and that is that vertex. Essentially, if we recall from 7.5, that h value, what we see in here, it's of the form x minus h. So we need to take the opposite of what we actually see in here. So I have plus 2. So what I want to do, instead of graphing this at the origin, I'm actually going to move it 2 to the left, the opposite direction, negative 2. And then I'm going to graph it. So what this horizontal shift does is it moves the graph horizontally to the left 2 spots, x minus a negative 2, or x minus h. H is a negative 2, our horizontal shift. But what if we have something like this? We have y equals f of x minus 3. So we're going in the other direction here. So our horizontal shift is actually to the right 3 units, plus 3. So instead of starting here at the origin, I'm going to go over to the right 3 spots and then graph my parabola. So we can see that that horizontal shift, what's inside these parentheses, shifts it either left or right, as we've seen in these 2 examples. And that's called the horizontal shift. It's how do we change x? Which direction do we move it? And it's always opposite of what we see in these parentheses, our h value. Now, there's another type of transformation or translation. What if we change a sign? Here we have y equals negative f of x. The function is negative. So that would be negative x squared. Well, our parent function, instead of opening up, as we recall from 7.5, our a value in this case of a quadratic is negative 1. When it's negative, instead of opening up, it opens down. And that's called a reflection across the x-axis. So instead of opening up, this parabola would open down. And that's called a reflection. When we introduce a negative sign as a multiple, it's negative 1, essentially, times the function. That's going to change it. It's reflecting it down. And why is that? Well, if we think about it, if I put in any value for x and I square it, it's going to be positive. If it's a negative value, a negative squared is positive. So all the values of our parent function were positive. Well, now we're saying we're going to change those signs. So all the y values are now going to be negative. So it reflects it across the x-axis, as if this were a mirror reflecting the parent function down. Now, there's another type of translation that we're going to see, and that's called the vertical shifts. This is, what if I take the entire function and add a value to it or subtract a value from it? Well, here, y equals f of x plus 2. So I take my parent function, x squared, and I'm going to add 2 to it. Well, any value that I put in for x, I square it and add 2, well, that's just going to move the graph up vertically. And that's why it's called a vertical shift. So my library function would start at the origin. Well, this function, I'm going to add 2 to it. So I'm going up 2. And then I just graph the parabola. So we see that it looks just like my parent function, except it's shifted up or vertically 2 units. If you recall from 7.5 again, this is our k value. K is the vertical shift up or down. And if we look at this example, what if y equals the function f of x minus 4? So we take our library function x squared, and we're going to subtract 4 from it. So instead of starting at the origin, we're going to move it down 4 units and then graph it. So we get the idea, right? Our vertical shift moves it up or down. Our horizontal shift, as we've seen, moves it left or right. And any reflection, sign changes, is going to reflect it through the x-axis if it's outside of our function, as we had seen here. All right, so let's see how we can use these translations to graph functions that may have more than one type of translation or transformation in it. Here I have y equals negative x squared minus 2. The first thing I'm going to graph, and I'm going to do this one piece at a time, is I'm going to graph its parent function. Well, the parent function is a parabola, some x value squared. So there is my parabola at the origin. The next thing I'm going to look at is this reflection. Well, what if I took this parent function and I reflected it? Because I have a negative a value, so I'm going to reflect it down. So my reflection is going to bring the graph across the x-axis as a reflection. And then if we see here, well, I'm taking my parabola and I'm going to subtract 2 from it. That's a vertical shift. That's going to bring it down 2 units. So from the origin, here I go down 1, 2 units, and I graph a parabola that opens down. So this here is a sketch of negative x squared minus 2. And I really didn't have to graph anything except for essentially one point. And that, in this case, it's the vertex. And we do our translation. We reflected it, and then we did a vertical shift down. Now, the next one, if we look at this, we notice, hey, there's no x squared here. So this is not a parabola. What is its parent function? Well, above it here, I'm going to write the parent function. The parent function is just the absolute value of x. That means no matter what value I put in for x, the y value, the output, is going to be positive. So if I were to just graph this, if I put in 0 for x, the absolute value of 0 is 0. So I get 0 for y. We're at the origin. And then for any positive value of x, I get a positive value of y. For any negative value of x, the absolute value of a negative is positive, I get a positive value for y. So it kind of looks like 2 linear equations. Y equals x, y equals negative x. And we can see that this looks like a v. This is the parent function of an absolute value. Now, if we look here, what are we doing to this function? Well, we're going to add 2 to the x value. It's within these grouping symbols. This is the same as an h. So it is a horizontal shift. If there was something out here, maybe plus 2 or minus 2 or some other number, that would be a vertical shift. But because it's in these grouping symbols, in this case absolute values, this is a horizontal shift. And we have to remember, it's always the opposite of what we see here. It's x minus h. Well, in order to have a plus 2, h would be negative 2. So I'm going to shift it horizontally to the left. So here my horizontal shift, instead of having this v shape at the origin, I'm going to move it over 1, 2 units, and then draw the general shape of that function. Now, these translations can actually be applied to any type of function, whether it's exponential or cubic or a square root. What we need to really know in order to apply these translations is to know our parent functions. Know what a cubed root function looks like. Know what a cubed function looks like, or a square root, or even an exponential or logarithm that we covered in the previous section, chapter 8. All right, the last thing we're going to look at in this video that corresponds to the notes is the difference quotient. Now, the difference quotient is just a new way of looking at something you should already know very well, and that's slope. The slope of a linear equation we know is y2 minus y1 over x2 minus x1, the rise over run. Well, this here, if we put it into function notation, now we can apply the same concept to nonlinear functions. Essentially what this says in function notation is this here is f of x, the same thing as y, right? So it's like our initial y value, y1. This piece here is a different y value at a new x, some x that's been horizontally shifted. So we're going to move down the line or back the line. Somewhere on the x-axis, we're moving to a different location. Well, when we change x, we get a new value of y. And that's what this is saying. We're going to change x by some h value. So this is like a y2 minus y1. Where we start, where we end up with. Well, the same thing here. This is our change in x. We have x1, which is our starting x, and some value somewhere else on the graph, x and some other number, maybe positive or negative, is just somewhere else on the graph. That's our x2. So our difference quotient is nothing more than finding the slope of a line. And we apply that to something called secant lines. Secant lines tell us the average rate of change between any 2 points on a nonlinear graph. So here I have some graph. It may be a parabola, it may be something else, because we don't see what's happening over here. We just see this piece of the function. So this is my first point. If we think of it as x and y, well, function notation is x, f of x. So that's this point right here. Here's my x value. Here is my f of x value, or my y. And then I'm going to move further down the line here. I'm going to add some value h to it. This is the h distance. It's h more than x was. This is my new x value, x plus h right here. And that's going to give me a new y value, or f of that value we're putting into the function. Now, if we use the slope equation, if we simplify this to get the difference quotient, well, we have x minus x. That just leaves me with h. This is the difference quotient simplified. We can just use that right there. It's the change in y over this change in x, which is just some h value, some horizontal shift left or right. So let's look at an example. We'll move over here. And what we have here is just f of x equals 2 minus x squared. And we're just going to plug it into this function here. All right, the first thing I want to find is f of x plus h. Let's actually put x plus h in here. 2 minus x plus h, and this value squared. So this is my new f of x plus h. From that, I'm going to subtract f of x in our quotient here. Well, f of x is this value. And it's always a good idea to use parentheses, because that would have to be distributed. So we have to remember we're subtracting this quantity. All over the change in x. Well, the change in x is just that value h. So we're just putting it into the difference quotient. You can memorize this, but you really don't have to, because you do know slope. It's just the change in some y value, the old y value, the new y value. You're finding their difference over the change in x, which is, in this case, some h value. Now, if I simplify this, I have to FOIL this quantity out, right? So if I FOIL that out, I'm just going to write here 2 minus, FOIL this out, I get x squared plus 2xh plus h squared. That's what I get when I FOIL this. And this value, I need to distribute the negative, minus 2 plus x squared. Negative 2, negative x squared. That changes the sign of here to give me x squared all over h. Now, there is some more simplifying. And because I'm running out of board space here, I'm going to move back over here. But now we can distribute this negative through here. And I'll do that just by removing these parentheses, which distributing that negative is just going to change the signs. So now I can just combine like terms. I have 2 minus 2. Hey, well, that's good news. Sums to 0. I have negative x squared plus x squared. That sums to 0. When you use the difference quotient, a lot of the times things are going to cancel out. And let's just take what's left here, because these aren't like terms, and it's over h. So I have negative 2xh minus h squared all over h. Now, in many of my videos up to this point, I always tell you factor, 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 factor. Recognize that there is something I can factor here, because we always have to reduce our fractions, so we should check this. Well, I look at this and say, you know what? Each term here has an h, so I'm just going to factor it up here. H factored out of this would leave me negative 2x minus h times h over h. Well, now I can reduce it. H over h cancels, and I'm just going to move up here. Negative 2x minus h. This is my difference quotient, which means I can find the average rate of change from some x value to some h value, regardless of what they are. This is the difference quotient. The difference quotient tells me what the slope is. What is the average change of rise over run? What is the average slope between any 2 points of a graph? Now, where could we see an application like this? Well, let's say we were driving a car from point A to point B. And during that time, our speeds change. So it's not a nice linear function. We're going to be increasing our speed and decreasing our speed in different speed zones. So when we finally get to our destination, we can use in our minds essentially the quotient rule, or the difference quotient, and basically say, what was my average speed? The distance I traveled over the time it took me to get there. And we could get an average rate. And that's what a secant line tells me. Even though I may have increased my speed from this point to this point, I had an average speed between these values. So the difference quotient has lots of applications when we want to look at averages that are nonlinear. So this has been section 9.1, Transformations and Translations. Please know your library functions. It will make this so much easier, and we'll see it over and over as we move on in this section. Thank you.